In this small chamber, there's almost no air. In fact, it's at 10 to the minus 6 millibar, which is 1/1000th of an atmosphere, or what satellites experience hundreds of kilometres above the surface of the Earth. And it's all thanks to this vacuum equipment I've bought and the control system I've built for it. The control system is made up of some hardware to electronically communicate with the vacuum equipment, and some software to monitor and control it. I'm doing all of this as the first step on my journey to build an open source scanning electron microscope. And without all of this equipment, there'd be too much air in the microscope's chamber, so electrons in its beam would constantly collide with air molecules and be scattered before they even get to the thing you're trying to image. So, what did I buy? Well, I got 2 pumps. The first is a rotary vane pump. It's full of oil, and it works from atmospheric pressure down to around 10 to the minus 3 millibar. Once you get there though, gases start behaving differently, and you need a different kind of pump to get to any lower pressures. That's where the second pump comes in. It's a turbomolecular pump. It uses a different mechanism from the rotary vane pump, and theoretically it should be able to get us down to around 10 to the minus 7 millibar, which is good enough for an electron microscope. There are 2 important things to note though. The first is that the turbo has a maximum operating pressure. If you try to run it at too high of a pressure, like atmospheric pressure, that can be a bit too much for the blades inside, and when they're spinning at 90,000 RPM, that's not going to be a good time. To avoid that, you first run a roughing pump, like this one, until you reach the turbo's operating pressure, and only then do you turn it on. That's why I need 2 pumps. This turbo's operating pressure is 18 millibar, which is well within the capabilities of this pump, so we should be fine. The second thing to note is that the rotary vane pump has something called an anti-suckback valve. And what this does is if the pump stops running for any reason, like if it breaks or there's a power outage, and air at atmospheric pressure tries to rush into the vacuum, the valve closes and stops it. This prevents the oil that's inside the pump from being sucked into the chamber and contaminating everything, and it prevents the turbo from seeing a huge pressure spike, which, as we just discussed, can damage it. So it's a super useful feature for the pump to have. So those are the pumps, but what else did I buy? These 2 parts at the front here connect to the rotary vane pump and capture any oil vapor that tries to escape. That's good because I don't want to be coating my walls with the stuff. This is the pressure gauge and its controller. It's a wide range gauge, which means it contains 2 mechanisms for measuring pressure, and it automatically swaps between them, so it'll work over the whole range of pressures that we're dealing with. Finally, we've got some controllers and power supplies to run all of the equipment, plus the bits and pieces we need to connect it all together. I bought all of this equipment secondhand and refurbished from Australian Vacuum Services here in Sydney. Shout out to Lawrence, who was super helpful throughout the whole process and really supportive of my ambitious and maybe slightly misguided project. If you want to buy equipment like this for yourself, it'll probably set you back around 15 to 20,000 Australian dollars.
15,000 dollary dues!
If you're willing to take a risk, you might be able to get it cheaper from places like eBay or government auctions, but just make sure it works before you buy it. Eventually, I want to be able to control the microscope and all of this equipment from my computer. Thankfully, we can talk to the pressure gauge using this serial port on the back of the controller, and we can talk to the turbo using this RJ45 port. In the future, when I plug the microscope into my computer, I want it to be a single cable. I don't want to mess around plugging in a bunch of different things. I'll also want to control various voltages and currents, so I'm going to build a custom controller to sit in front of it all. For that, I'm going to use a Raspberry Pi Pico 2. I'm sure I'll need something beefier in the future, but this will do for now. On the Pico, I'm going to write software in Rust and use the Embassy framework. I chose Rust for its type safety and multi-threading support. Embassy leans into these async features, and also just seems like the most popular embedded framework. I found it pretty easy to get started with Embassy. Here I've written a program to turn the Pico's built-in LED on and off, and send some log messages through the debug probe. I can compile it, upload it, and it works. With tooling out of the way, now we're ready to communicate with the vacuum equipment. Let's start with the pressure gauge. The controller manual says we can send it a message and it'll send a response. The messages use ASCII characters, They start with an exclamation mark or a question mark, and they end with a carriage return. If the message starts with an exclamation mark, we're sending a command, we're telling the controller to do something, and if it starts with a question mark, it's a query for some sort of information. If we scroll down, we can see the commands it supports. For example, we can set the units that pressures are expressed in. And a bit further down, we can see the queries it supports. For example, we can read the gauge pressure. That's one we'll use a lot. Or we can read the units that we're currently using. Okay, seems simple enough. The only problem is that the controller communicates over RS-232. The Pico's UART transmits 0 volts for a binary 0 and 3.3 volts for a binary 1, but the controller transmits less than -5 volts for a 1 and more than +5 volts for a 0. Not only are these inverted from the UART, these voltages are too high for the Pico and they might damage it if we connect it directly. To solve this, I bought an RS-232 level shifter, which should do the trick. First, let's test that the Pico's UART works as expected. I've written some code to repeatedly transmit the capital letter A. I'll hook an oscilloscope up to the transmit pin and make sure we see the right signal. In ASCII, capital A has a value of 65, which is this in binary. But the bits are transmitted from least to most significant, so we'll actually see this on the oscilloscope. I've hooked everything up so I can capture a trace. If we zoom in, you can see we got a start bit, followed by 1, 0, 0, 0, 0, 0, 1, 0, and some stop bits, which is exactly what we expected. Also notice that the signal goes from 0 volts up to the Pico's logic level of 3.3 volts. Next, let's connect the converter to the Pico and see if it outputs what we expect. I'll connect the oscilloscope to pin 2 of the serial port, which is the transmit pin. Now we can capture a trace and see what we get. Okay, it looks like this signal jumps between plus and minus 6 volts, which is much higher than the Pico's 3.3 volts. And remember that RS-232 transmits positive voltages for zeros and negative voltages for ones. So here we have a start bit, followed by 1, 0, 0, 0, 0, 0, 1, 0, and some stop bits. Which is great. That's still a capital A, it's just been adjusted for RS-232. With that all working, now we should be able to communicate with the pressure gauge. I've written some code that sends a message asking for the current pressure, waits for a response, and prints the result. Let's see what happens when we run it. Okay, that didn't work. It looks like the read timed out after 500 milliseconds, which suggests we're not getting anything back. Let's make sure everything's connected properly. We know from our earlier testing that the signal's definitely being transmitted on pin 2. But what does the controller expect? Okay, it's also transmitting on pin 2, so the devices are just kind of yelling at each other and neither is listening. To fix this, we can use something called a null modem adapter that swaps pins 2 and 3 internally. With that plugged in, let's try running the code again. And this time we get the pressure back. Great. So queries are working, but what about commands? Let's try changing the pressure units from millibar to torr. If this works, we should see the unit change on the controller's display. And it does. Awesome. With that, I think it's fair to say we can talk to the pressure gauge. Next, we've got the turbo. Looking at the manual, this one's going to be a little more complicated. It uses RS-485, which is a bus protocol, rather than point-to-point like RS-232. That means you can have several devices connected and they can all communicate. In this diagram, for example, they've got a PC and presumably 2 turbo controllers all connected to the same wires which form the bus. Unfortunately, the Pico's UART isn't compatible with RS-485 either, so I've got another converter. As for what data actually gets sent across the bus, we need to look at this protocol document. The messages are ASCII again, which is good, but they need to have a particular structure. It starts with an address, I guess so each device on the bus can tell who the message is for, then an action, whether we're reading or writing a parameter, the number of the parameter we're interested in, some associated data, a checksum for the whole message, and a terminating carriage return. Fair enough. Should be a simple matter of programming. Let's start by connecting the converter to the Pico. This is pretty straightforward. The only interesting thing is that the converter outputs a 5-volt signal, which is too high for the Pico, so we need to reduce it using a couple of resistors. With that done, now we can set up the bus. RS-485 uses differential signalling, which means there are two wires and the signal is encoded in the voltage between them. To avoid noise, we need to keep that voltage at a known level even when no one is transmitting, so we'll add pull-up and pull-down resistors. We'll also chuck a termination resistor between them to minimise reflections of the signal. To test our circuit, I'm going to continually transmit the capital letter A again and see what appears on the bus. I'll record traces from both wires. Okay, good, it seems like something's being transmitted. Now I'll calculate the difference between those two to get the actual signal. And again, we get the binary for the capital letter A. Great. Now we can try to talk to the turbo. I'll hook up this RJ45 port so we can access the wires we're interested in and connect them to the bus. But what parameter will we read? This table lists all of our options. We want something simple to start, so how about its operating hours, which is parameter 311. We need to craft a message in the format we discussed earlier. The turbo's address is 001, we're reading a parameter, the parameter number is 311, the message data is an equals sign followed by a question mark to indicate we're asking for the parameter's value, and I've calculated the checksum manually. So we send that message, read the response, and extract the response data, which should be the total number of hours the turbo has run. Okay, let's run this code and see what happens. Great, it worked. It looks like the turbo has run for just over 38,000 hours, or over 4 years, so it's definitely had a life before coming to me. Okay, so we've got a working prototype, but this breadboard is a bit of a mess. I designed a simple PCB to tidy it up a bit. It has headers to mount the Pico and the RS-485 converter, connect it to the RJ45 port, and connect it to the RS-232 converter. I sent off my design and the PCB arrived a few days later. I soldered all the components onto it and connected everything up. That's a bit better, but everything's still out in the open. So I designed a case in Fusion. It has holes for the cables and threaded inserts so I can mount all of the components. I 3D printed it and put everything inside. Okay, great, that's much better. Now all that's left to do is write the software. Okay, so how is this going to work? At a high level, I'll have a program running on my computer that wants to control the vacuum equipment. My computer will be connected to the controller, and the controller will be connected to the vacuum equipment. The program will want to exchange messages with the equipment. Say it wants to read the current pressure and turn the turbo on. The controller can't tell the difference between pressure gauge messages and turbo messages, so if they were sent in their raw form, it wouldn't know what to do with them. To avoid that, the program will add a prefix to each message indicating its destination. When the controller receives one of these messages, it'll inspect the prefix, remove it, forward the message to the correct destination, and return any response back to the program. Make sense? Good, because this is the firmware for the controller. I won't explain it in detail because that's boring, but it does exactly what I just described, plus some stuff like handling errors, timeouts, and USB disconnects. If you actually want to read the code, it's on GitHub at the link in the description. That's the firmware done, but what about the program running on my computer? Well, we don't actually know what that will be. Maybe there'll be multiple programs that want to do different things. There could be a program to calibrate the microscope, another to actually use it, or something I haven't even thought of yet. To play it safe, I'm going to write a reusable library for communicating with the controller and equipment. And here it is. This is the interface for the pressure gauge. You can see we can request the current pressure, or change the units it uses to represent pressure. And this is the interface for the turbo. We can request things like its current draw, rotation speed, and operating time, and we can turn it on and off. Again, all of this code is available on GitHub if you want to read it in more detail. Let's see a program that uses this library. I've always wanted to build a terminal UI, and it'll be funny to graph the chamber pressure in the terminal, so let's give Ratatouille a go. This is what I came up with. On the left, we're graphing the chamber pressure over time, the turbo stats are on the right, and there's some shortcuts down the bottom. If we try to turn the turbo on at the moment, we get an error message saying the chamber pressure is too high. That's good, it stops me from doing something stupid. I'll turn on the roughing pump and wait for the pressure to drop. So we can see that the pressure is dropping, but this graph has very quickly become useless. We can see the current pressure up the top left here, and around 15 seconds after turning the roughing pump on, we're already below the turbo's maximum operating pressure. After 2 minutes, the y-axis is updated, so the graph is a little more useful, and we're sitting at around 5 millibar. Let's turn the turbo on. It's asking me to confirm that the roughing pump is running, which it is. We can see the turbo started drawing a current and its rotation speed is increasing. After 3.5 minutes, the pressure is dropping so fast that the graph is useless again. We're at 2 times 10 to the negative 4 millibar, and the turbo is only at 50% of its target rotation speed. After 5 minutes, the turbo has reached its target rotation speed. The pressure is an order of magnitude lower at 2 times 10 to the negative 5 millibar, and it's still dropping. After 12 minutes, we're into the 10 to the minus 6 millibar range, and the pressure is still dropping. This should be good enough for an electron microscope, so let's leave it here. Here's a more sane graph of the pressure over time on a logarithmic scale. You can see where I turned on the roughing pump, where I turned on the turbo pump, and that we'd probably get a bit more of a pressure drop if I left it running longer. As funny as I find this terminal UI, it probably won't work for the final microscope. It is a good demo though, showing how you can monitor and control the vacuum equipment from a computer. This is just the first step in what I expect will be quite a long journey. The next step will be to design and build the microscope's electron gun, and here's a little sneak peek of how that's going. This is a simulation I'm building that lets me tweak the geometry of an electron gun and see how it affects the electric field and the electron beam. I'll talk more about this in my next video. As I mentioned earlier, all of this is open source and available on GitHub at the link in the description. Feel free to follow along there or subscribe here if you'd like to get updates. Thanks for watching.